Hi, class. I want to talk about activity two. And so if you go to Canvas and you open up activity two, then you'll see the file. And this is our second topic of the course, and it's on using grids. And you guys are familiar with that, but we're going to talk more about just kind of math-based grids. And sometimes people use very simple grid system. Sometimes people think like, rule of thirds, or they break things up evenly spaced and they use to transfer an image from a photograph over onto a canvas or something. And so there's different reasons for using grids, but we're specifically just going to talk about some different ones, and there's some different ways you can use that are kind of grounded in math. And I really want to talk about the most popular one when people talk about a combination of math and art. And so that has to deal with this idea of the golden ratio. And so I'm going to just kind of answer. I'm not going to go into all of these sites. I put these links in here, as you know, to help you find the answers. But some of these will be a lot faster just for me. I'll talk a little bit about it, and some I'll bring in the um, websites and so on. But so what's the exact value of the golden ratio? And I'm going to kind of move us over a little bit. Okay. And I'm going to uh, write on the tablet and also just kind of go back and forth. But the it says number one, what's the exact value of the golden ratio? And so it's 1 plus the square root of 5, all divided by 2. So sometimes I use this little symbol here. The 1 plus the square root of 5, again divided by 2. So it's written as a symbol, and not typically as like a decimal approximation, but this is the exact representation. So we don't have an exact decimal representation for this golden proportion. And because of this square root here, a square root uh, that gives us an irrational number. And the irrational numbers are numbers that are non-terminating, non-repeating decimal values. So that means that the decimals kind of just keep going out, right? And so this one does too. And if we bring that file back up again, so this 1 plus the square root of 5 divided by 2 for number 1. And what's the approximate decimal value of the golden ratio? So in other words, I want to take and convert this over to a decimal. And if you take your calculator, I'm just going to pull this up. And if it opens over here, all right, so I'm waiting for that calculator to open. And let's see where it's at. All right. So I'm going to clear all this stuff out. So if I take this and I'm going to put parentheses, so 1 plus, and then second function square root, right? 1 plus the square root of 5. And parentheses. That's the numerator here, so I'm going to divide it by 2. So we're going to go divided by 2 and hit enter. So we get this 1.618. Then there's a 0, 3, or so on. So if we rounded this, it would just be 1.618. So we're going to stick with that. And so So this phi is approximately equal to 1.618. Right? Now, um, the idea is that it's a ratio, though. So this first way it's written over here, this is a ratio is a comparison of two numbers by division. So we think about numerator and denominator. So here's a number up here, here's a number down here. We're comparing these two things by division. So that's where we get the ratio at. So this right here basically is referring as 1.618 to 1. Okay. And so when you work with that, that's what they're referring to, this 1.618 to 1. Now, you can use that as either multiplying or dividing with numbers to figure out how you can maintain that ratio, okay, when you're setting things up. So first of all, uh, let's take a look at, historically, I like to look at the concepts, and this golden ratio has been around for a long time. It's had more kind of attention combining math and art than anything else. And this is even throughout history. So this has been around for a long time. List 5 historical places. And so if we take, and I'm going to put that in here. Bring this over. So early history, they talk about ancient and medieval architecture, and in Greece and Mesopotamia, Islamic architecture, Buddhist architecture, Romanesque. So it seems like, early history, there's a lot involved in architecture, like the Great Pyramid of Giza in Egypt. So these are thousands and thousands of years old. And they supposedly, talked about this proportion. And they say authors have claimed early monuments have golden ratio proportions and conjectural interpretation. So if you read the history, some of it's a little sketchy, but the idea of it has been around. We know that Pythagorean was around BC, and he had written about it and talked about it, and this special ratio. And that's why it was used initially, because people thought it had these special properties that other ratios didn't have. And um, they have another one in Greece here. You'll see this was in BC, the Parthenon. Uh, the building of the Parthenon, they would use the proportions of the golden ratio to create the sizes and so on. And here's another one, and this mosque, Quran, and Tunisia, and so on. And then in the times of Gothic architecture too, back in the 1200s, here's in the 12th century, here's Notre Dame, one of the most famous buildings and stuff, using these proportions of the golden rectangle. And so we see this kind of all throughout history. Even today, we see a lot of the proportions. And why again? Well, we'll get to that in a little bit. But so number 4 on the pull this back. Number 4 says list 5 different historical places golden ratios have been found in art. Okay, so we got architecture and then art, and there's talk about the Leonardo da Vinci and the Vitruvian Man, and then some people say, well, maybe not, it doesn't quite fit. But again, we're not too concerned about that right now, whether these old things that fit. Uh, the George Seurat talked about the golden mean and used that in a lot of his famous paintings. Cubist painters, uh, had conversations about the golden ratio and its significance, and um, they said possibly, Marcel Dion and so on introduced these ideas, but we can look throughout and find several people, though. It's just not like one or two or whatever. There's been lots and lots of talk about the golden ratio in architecture, in art, uh, and then here's 5 different things from nature where the golden ratio has been found. And a lot of people talk about this. And there's some examples here again. It says many examples of the golden section are divine proportion in nature. And then they say these lengths here of the dolphin and then the markings on the butterfly, the shell, the spiral of the shell, and so on. So you have fish and penguins and all this. So a lot of the talk is there. Okay, the talk. Does this work out exactly right? I don't know. I don't know if that's really important to us right now. I'm trying to emphasize the idea that the golden ratio has been talked about in lots of different ways throughout history. So it is something that you really should learn about and maybe even use. And so uh, another area, number 6, it says, what is Dave Steele? It was just an art style. It's called the style, but a lot of it had to deal with um, golden proportions and so on. And again, these links, I'm not going to open up all of them. I will open some of them up and take a quick look. But Mondrian and was one of the more famous ones, and Rietveld, and it was simplicity. This idea of things being very simple and clean, and there's the golden proportions are within the distances in these lines, so it is within this here also. Even though it just kind of looks like some random lines here and there. Uh, People felt like it was special and that it could help make the pieces special. And so nobody really argued much against it. They just thought it was kind of neat to use at times. And so now, so again, we know that it's gotten a lot of attention, a lot of attention. Okay. And does it warrant that attention? Well, it just depends on, your philosophy. And is it special? Well, it does seem to work in some senses. And for example, here was an experiment that was done years ago. This is just a rough idea of what really it was like. But they took a bunch of rectangles of different sizes and shapes and so on. And they asked people, they said, okay, which one do you like the most, right? So some people said 1, and some people said 2, and some said 3 and 4, and so on. And so not everybody picked one particular rectangle. And, it wasn't like obvious, though everybody loves only the golden ratio, the golden rectangle, and nobody likes the other ones. And that's not what they found out, right? And if you take and measure the length and width here, you're asked to take and measure how long it is here, put the length in for rectangle 1, and then the width, you measure the width, and if you have like a ruler or something, you could measure in millimeters or You can use a grid system. And then you take the length divided by the width, and you'll get a number here. So for number one, right, when you divide the length of it by the width, you're going to get basically 1.618, right? So if you measure accurately, this is the golden rectangle right here. These other ones deviate from that value, okay? So what came of that, and what do we want to look at from that result? And basically what I want to show you is this. Again, the results, when the data was collected, and just not this experiment, but other experiments too, the results were normally distributed, okay? So we have a normal distribution with a mean of 1.618, okay? So the ratio of the length divided by the width, right, was calculated for all the different rectangles, and then they took and found the mean of what people liked. And it ended up being this golden rectangle, right? This golden proportion, 1.618. And as you go and deviate away from that, so as you deviate out and you get more towards the rectangles that were a lot longer than the width, like twice as long, like up here would be 2 times as long, 3 times the length being 3 times longer, like a long, skinny rectangle. What this means is as you deviate away from the middle, the people that chose that went down dramatically. Okay? And on the other side, as you deviate down the other way, okay, which these are kind of symmetric here, but as you go the other way, the results of what people liked went down dramatically. So we have some empirical evidence that there does seem to be something there, and that if you're looking to create something, now let's say that you are trying to create something to satisfy as many people as possible. You know, you're building a game and you want things in there, characters that people like, and so on. And, you know, part of that's going to be the size and the shape that you build things in that. So if you want to have characters that are pleasing to people, well, there's enough of research out there to show that if you follow this, you're not going to please everybody, right? That's not what I'm saying. But the masses, see, if you deviate very far one way or the other away from this, they're not going to be pleasing to people. Now, you don't want all your characters to be pleasing. Some of them are going to not. They're going to be the antagonists and the ones that people don't are going to like, and so on. So then, obviously, those ones you don't want to have in these proportions. So you want to be out away from there more. And so that's how you have to kind of think about it, is that what do I really want to do with this? Do I believe in it? Well, it doesn't matter as much as you just need to understand what's going on. You don't have to believe everything everybody tells you that, you know, the fish and the koala bears and all that are all the golden ratio in nature and stuff. And again, I don't know if I believe that or not either, but it doesn't matter because again, we're talking about design. So it's very important that you understand that if you're doing something which typically you're trying to maybe maximize some particular position, then you should be considering when you proportion something that people typically like. And I'll give you an example of another experiment that also matched this. There was an experiment done where people were just given a line and they asked the person, they said, put a mark on that line somewhere. Just anywhere, just put a mark on it. So somebody would randomly come up here and say, okay, right there. Now, if you take the distance from here to here, okay, we'll call that A, and the distance from here to here, we'll call that B. But basically, what came out, very tight distribution, okay, but A divided by B, okay, so this length, again, divided by this length, right, was approximately always around 1.618. So this distribution was even tighter. So we go up in a peak very quickly and come right back down. In the middle, again, was 1.618. And as you deviated a little bit from that, right, not very many people deviated very far. Not too many people put it in the middle. It was usually, this side or this side, but when you measured the longer divided by the shorter, it basically was right around, this value. So again, there's something, we have these different kind of things that seem to support it. Okay. So let's go ahead and take that off. And oh, there it is. Okay. All right. So the history, again, the history, we know that people have used it a lot. You can go online, look up, tons and tons of examples. They talk about it even in the Bible, that the dimensions for the ark. I read about things like the earth has murmurs. The actual center of the earth murmurs at a frequency that comes out to be basically 1.618. People talk about it and just all kind of crazy things nowadays. So it's not going away. In fact, it's the opposite. It's here to stay, and it's all around you. As you go and you walk around, and try to think about this at some time. When you walk around, you are exposed to the golden ratio every day of your entire life. So this isn't something that you don't know about. You unconsciously have had this thrown up in front of you every day, pretty much of your entire life, all of the time, which is remarkable. So you need to kind of figure it really is important that you learn as much as you can about it. And we're just going to briefly talk about it right with this activity. But um, so, well, let's think about that. Find 5-row items from everyday life uses the golden rectangle. Show the length and the width, each item in millimeters, then find the ratio by computing the length divided by the width. So again, you're going to find an item. Okay, so for assignment 1, you're going to find something that looks like a rectangle, and you're going to measure it. You're going to take the length, write it down, and then the width. Then you take the length divided by the width, and you'll come up with some value. And you want it to come up with basically 1.618. So we're trying to find items that are a golden rectangle, right? So I'll give you one of them, like a credit card. If you measure your credit card, it's by design, it is a golden rectangle, okay? So if you measure the length divided by the width, you will get 1.618, okay? Or very, very darn close to that. A writing tablet, I have one in front of me right now. If I measured this writing tablet, it looks very close. I know it would be very close if it wasn't. My my laptop is a Samsung. My pad, it looks almost exactly. If I measured it, I would almost guarantee you that that pad in front is a trackpad is the golden rectangle. My graphing calculator screen. Now I don't know about this one that shows up on here, but when the TI calculator came out, they on purpose designed the screen to be a golden rectangle. And I bet if I measured this, it looks pretty darn close. and so on. So, but what you want to do is look around at things, products, tables, papers, awards. There, there's so many things in life that are rectangular. You'll be surprised if you go to the store and you buy a bag of Oreo cookies that package is the golden rectangle. Um, it's all around you all of the time. And so it won't be hard for you to find 5 items. All right, so we're going to move past that. So again, it really is here to stay. We could go online and find, if we had the time, we could easily find 1,000 things that exist out there in our world that were constructed using the golden rectangle. So if you're in design, if you're in art and design, I mean, you're going to be using it. You should be, not all of the time. That doesn't. I'm not saying that that's has to be done or used all the time, but you should be using it because people are going to expect you to use it in a lot of cases. And we're just going to look at a couple here. This says, give an example of how golden ratio can be used in furniture design. Now, I want to pull this up because I don't want you to think that everything is a rectangle. Okay, that just happens to be the most common thing only because the world around us uses rectangles so much. But there we are. Okay. All right, so here you can just take a look at, I'm not going to go through, but they say this, ratio of this length to this length. And we kind of just talked about that with that experiment, but if it's 1.618 to 1, or you take whatever this is times 1.618 to get this, then, uh, they would be in that right proportion. But, we're not talking about these rectangular drawer faces. What I'm talking about here is that this height. So this height to this height divided by this distance to this distance is showing feet. It's equal to 1.618. And then this height to this height divided by this height to this height, 1.618, and so on. So there's just another example of where people, can use that at. Find an online image that incorporates the golden ratio. So you can go online and find things. And I want to show you this one you're all familiar with, hopefully. But you see, in Ringling, the Ringling College of Art and Design logo, this rectangle right here is a golden rectangle. Okay. Now, I actually had input into this design several years ago, and now I didn't propose the golden rectangle, but I said we have to have art or math in there somewhere. And then one of the other ladies that had been here for a long time, she said, "Why don't we look at that as a window?" So that's supposed to be representing a window into this creative design thing. But good, I think that's neat. Um, and you can create grids with this proportion, and so that one of the things we're talking about is having grids to create. Now here's some simple stuff. Now it says list two programs. This is called a trace. ATRSE is one, and it just kind of was supposed to lay over anything. So whatever you're working on, you can bring it in and lay it over the design and see if it matches up. So, or phi matrix is another one that you can lay over top of this. So here's like a simple shirt, and you'll see like here's a golden rectangle right here, and they're showing I cut one of the dimensions off, but this would be a square, and then this right here would be the other part. And now in reality, when that happens, then this rectangle right here is also a golden rectangle. Okay, so one of the properties. And then again, you can see here the rectangles and how they laid out these distances and so on. So, um, so we have grids, or you can make up your own. Um, and let's look at this. It says construct a golden rectangle using a compass and ruler. And so we're going to do that. And here we're going to get to. I'm going to show you how they created, this spiraling thing, like right here with these flags. We're going to put that down for a minute, and I'm going to. All right, go to the thing. So if you want to construct, so this is where the geometry comes in. And again, I'm just going to rough this with my hand. I do have a ruler down here I could use. I'm just trying to save a little bit of time because that's slow. But if you take and you get the dimensions, okay. Now what you need to do is you have to start out with a square. Okay, so there's my square. And then I go to the midpoint here on the bottom. So you got to construct the square first. Then you go from here and you draw this line from here up to here. Okay. Now with a compass, you would put your compass from here to this corner up here. All right. And then you would rotate this down this way. Okay. So again, this is kind of just I'm just trying to speed this up, but basically, and again, this drawing pad's really kind of hard to draw on, but I would have this arc, and then I would extend this line out, okay, to wherever this point would hit, and then I would extend this straight down, up, and across. And maybe I should have used the ruler because that's really bad. Okay, so again, so this rectangle from here to here, and from here to here, all right? And next time, I think I'm gonna use this, and I need the mouse. I think that. All right. All right. So yeah. The next one I do, I'm going to actually use my ruler because that'll look a lot better. Um, and then, so the construction again is pretty easy. So we're going to start, and I'm going to go ahead and all right. Now, okay, at least that looks a little bit more like a rectangle. Okay. All right. And now, so let's assume that that is a golden rectangle. We did the construction. All right. Move this up out of the way. And I'm going to zoom in on that. Okay. Now, we do a lot with these, but one thing that you can do is uh, there's not something else special about this rectangle, and this will not work with any other rectangle. And you have to be pretty accurate, and I think that's why a lot of people think this one has got special properties. But I'm going to, again, I'm not doing this to scale exactly, but uh, if I draw a square, if I draw a line in here, okay, so I form a square. Now this rectangle that I end up with is also a golden rectangle. Okay, so it maintains the proportion. All right, so I'm going to do that again. So I'm going to come down and draw this. Okay. So again, what I did is I created another square here. Well, what was left over here is a golden rectangle, another one. So what they talk about is that you can continue to create more and more smaller overall size, but maintaining the proportion. So you can get smaller and smaller. You can get whatever size rectangle you want. Basically, you just keep kind of going in on this, and I have to keep turning this thing with my mouse and do this again, and so on. So okay. So once again, square here. This becomes a golden rectangle, smaller size, same proportions. And then I'm just gonna speed this up here. So again, let's say we had one here, was next, and here, and here, and here, and so on. Okay. All right. So we have this infinite. This goes on to infinity, right? So we have this infinite block of these golden rectangles that just keep getting smaller and smaller. So that is a very special property about this 1.61821 that works. And that's where this came from here. So notice the flag. Here's the square part. This was the overall rectangle to start with. Then they built a square, and then they made another square here, and then here, and here, and here. And so you kind of have that spiraling in. So that kind of extended the idea. They talk about a golden spiral. So we had talked about the golden rectangle, just lines being certain proportions apart. And then now it says construct a golden spiral, okay, from what we just created. So that means you can take this thing, okay, and again, this is going to be not that great, but we're going to try this anyway. So I'm going to start here, and if you had a compass, you would put the compass point here and arc this down to here, this point. And then you would move your compass point to here, and you would arc this up this way to this point. And again, you keep moving your compass, and you keep arcing it around this way, and so on through those, off into infinity. So there's my golden spiral that is created from this golden rectangle, this repeating of the golden rectangle. So now we have another shape that people really like to use and talk about. So that's where this one comes from. And then you can see it kind of looks like this. And here's an example of where that might be used. So they have a picture here, and you'll see this thing would start up here. It would actually spiral down through here, come up, and curl around right to the focal point. So a lot of times people like their focal point, it would be right in here where that spiral ends. So again, it's here, comes up around, and it would curl down right into these grapes where this fox is looking up. So that's would be the where you would put that. So it turns out real nice. It's just a nice way to create a composition. All right, so list 3 other uses of the divine proportion. And I'm just not going to pull this website up. I want to speed this up a little bit. But when you go in here, you'll see that there's things like the golden triangle. Okay, another geometric shape, a golden triangle. There's the Penrose tiles are in there, and then there, of course, the golden spirals in there. They talk about, and then there is also the pentagram. But a pentagon is a geometric shape, but a pentagram has the lines in through it. But it's one of the richest forms of the golden ratio. So the pentagram was actually the symbol used by Pythagoras thousands of years ago in his secret society of the Pythagoreans. And they had this symbol, the pentagram, and because of it having all of these special features of it, in particular the golden proportions. So in mathematics, we find it a lot. For example, here, solve the equation x squared minus x minus 1 equal to 0. So I'm going to clear out that awful looking spiral, okay? And I'm going to put this thing back away. There we go. So if you remember some algebra, if you look at x, okay, x squared minus x minus 1 equals 0. So quadratic equation, a little algebra lesson, if you remember how to solve these. X was equal to opposite of b plus or minus square root b squared minus 4 times a times c, all divided by 2 times a, right? So x equal to the opposite of b, this is 1, plus the square root of b squared, again, this is b squared, 1 minus 4 times a, which is this coefficient, times c, which is negative 1, all divided by 2 times a, which is 1. So x equal to 1 plus the square root, 1 minus 4, this is 1 plus 4, right? 5 divided by 2, right? So there's my golden ratio, right? That's my exact representation of the golden proportion, okay? So we can even see that in as a golden parabola. So even if you're working in mathematics and you want shapes that relate to, you can use a parabolic shape with this formula. And remember that has that kind of shape that looks like this, right? A parabola, right? So you can have a parabolic shape involved using the golden proportion or phi. There's lots and lots and lots of different things you can look at. If you look through the site of 2 alternative math ways to represent the golden ratio, there's a lot in here. Sequences, series, and one of those I do want to talk about. So again, you could kind of take a look at this, but they have recursive functions, trigonometric functions, and they show that they all do relate to the golden proportion. So number 15, what's the Fibonacci sequence? Because that's the one that people typically understand. So Fibonacci wasn't a mathematician, but he did a lot of stuff. And he was in trade and shipping in, I think, Northern Africa and Europe and stuff. But he liked drawing maps, and he would mess around with some puzzles and things in math. But he ended up coming up with this sequence. And how does it relate to the golden ratio? Okay, so we're going to clear this again. So the Fibonacci sequence was a sequence of numbers. Now, some people started at 0, some started at 1. So 0 plus 1 is 1. And then you take this number plus this number and write the next number down. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 and 8 is 13. And so on. And this goes on and on. Now, why is this, what does this have to do with the golden proportions? And what it has to deal with is it's a recursive geometric sequence, but it's a recursive function. So if I drew this thing out, if I take this divided by this, okay, well, that doesn't work. Okay. But if I take 1 divided by 1, I get 1. Okay. So I'm going to start down here. And then if I take 2 divided by 1, I get 2. All right, so I'm up here. Now 3 divided by 2 is 1.5. I'm going to put that there. 5 divided by 3 is equal to, that's 1 and 2/3, so 1.66. So we're above a little bit. And then 8 divided by 5 is 1.6. Under, but you can see what's happening. This number is approaching, right, this line here, which happens to be 1.618. Okay. So when we draw the function, right, it's a converging sequence. So it converges onto 1.618 as you go through and get further out this line. So people are like, that is, okay, one thing that's interesting, right, mathematically speaking. So these numbers, we're going to keep those and then look at something else. So, all right, so so we got 15 and 16. What's a fib? 17. Control C. And okay. All right, the fib review. The fib is a poem, okay? It's a Fibonacci poem. It's a poetry form based on the structure of the Fibonacci sequence. So here's just like an application, again, another creative application of that proportion. We're starting to expand out away from the typical, a golden rectangle, right? People just used rectangles for a long, long time, and that was like all they ever did with the golden proportion. And then we started to see people be more creative, and that's how this stuff goes. Like it's, some of it is just because people were bored with the old stuff and wanted to branch, but some of it is because of the computers, and it just builds. So here's a poetry that has to deal with either the words themselves or the syllables, of how many syllables are in the word. So a good Fibonacci poem would have a sequence of syllables in their words, 1, 1, 2, 3, 5, 8, and so on, where it would go up and then back down. Okay. So let's take a look at this. So here's an example. So again, what's a fib? We're going to do one here. Um, I am in math class. So again, this is 1, 2, 3 syllables. I am in math class. And then the next line would have 5. Making this great poem. Okay, so that's 5 syllables. Next one's 8. With the Fibonacci sequence, right? So we're counting the syllables 8, and then it would get back down the other way. I found this cactus fits sequence, nature, math. So that's a good Fibonacci poem, and it's got a picture attached to it. Okay, here's another one. This is again, we're adding to the Fibonacci poem, we're adding a picture with it, because we're doing visuals, right? We're not worrying about the English as much as the visual going with it. So my large, so 1, 1, winding is 2, alien 3, your winding gold walls look so strange paired with my blue eyes. So again, Fibonacci, right? It's a Fibonacci poem. And so for assignment 3, so you guys are going to create a fib that includes a related picture. So just like this, so you're going to make your own Fibonacci poem. Okay. Okay, now I want to take, and again, the idea is that we want to be creative with these things. How do we take this stuff to the next level? So we got a fib, and what can we do with that or add to it? How can we add another dimension? We talked about dimensions, and we think about things maybe where we can expand or grow or make them better, add something to them. This is actually very interesting. This is a musical group called Tool. You may have heard of them. And this is Tool's Lateralis. And I'm not going to play the whole thing, but you guys are going to be able to watch this on your own. But make sure you go through and follow the words. They talk about the relationship between the song and the Fibonacci sequence. Okay. And there's other groups out there. Something Go. You probably know the group. I'd have to look it up. But it's something Go. They also do a lot of math in their music. Okay, I'm gonna speed this up. Okay, they're counting here, showing you the Fibonacci kind of sequence thing here. So if you understand the fib, then you understand how they created this song using the Fibonacci sequence. So again, you'll see it count up 1, 1. Or they're going down here. So okay, so again, that's something that's kind of neat, and it's hard to understand how much math it really is used in a lot of things that are out around us. But I had heard this song before, never knew that the Fibonacci sequence was in that, so I read about the group. And all right, so other current examples of the golden proportion, advertising, and years ago, the Greek statues were supposed to be the perfect body, face, head, everything. And there's a handout on Canvas that you can look at if you're interested in it. But uh, these were the proportions, and how you figured that out is in the handout. So if you wanted to create the perfect face, basically, this is what this is showing here. Now in advertising, they really do that. this face right here, this is supposed to be the perfect face. So when they interview even people, how do they decide who's going to be on their covers? Well, Estee Lauder, they actually measure the faces because they want them to be in. I'm not saying for all the advertisements, but for this one in particular, they wanted the perfect face. And if you measure using these rules, you'll see that the distances like between the eyes and then the lips as compared to the length of the lips to the width of the nose and all that kind of stuff from the eyes to the lips to the top of the head. All these things uh, basically come out to 1.618, or most of them. So advertising uses that. Logo designs, there's just tons of logos. I just saw another one, Google. The new Google logo uses the golden ratio. Uh, Pepsi, Coke, Apple, all the largest. Why do all the largest companies in the world, Toyota, Nissan, why do they use the golden proportions? Well, I don't know, but they obviously think there's something special in them, and you got to know that it would, that's just making you more employable when you work with designs. If you understand how much that is out there, it's extremely important that you understand how you can be creative as you move forward. And I'll give you an example here. The golden ratio in 3D is where we're kind of at now. So we know that the historically we've had this ratio around for thousands of years. We know we still use it today, okay, for a lot of similar things. But we're starting to push the envelope with other things like poems and music, and the logos are more traditional kind of stuff. But the three dimensions is slowly coming in now, where people are starting to do things in 3D. And this gives you some options you can look at. I'm not going to, open up and go through all of this stuff that you can look at on your own, but I want to talk about how do we create golden proportions in 3 dimensions, and can you create a golden cube? We know we can create a golden rectangle. How do you create a golden cube? All right, well, you can't. Okay, so then what? The rectangle was fine with 2 dimensions. What do we do with 3 dimensions? Well, again, this stuff kind of works together. So with geometry and design, because if you look at this picture right here, you'll notice the Mayan-like kind of 3D animation kind of building of these quadrilaterals in a sense. But the angles they draw in because they know that in reality to get 3 dimensional depth, right? You're pushing those things in, making it look like they're being drawn in and creating the face. Well, a guy named Stephen Marquardt years ago was a plastic surgeon, and he wanted to be able to pull up images of people so that he could get them to see what they would look like in reality, in a 3 dimensional reality after the surgery. And so we had this connection between the math because he had to look in to see how mathematically can you do that. It's just not, realistic to think you can draw all this stuff by hand and have it be accurate. So he worked on what they call this 3 dimensional mask. So he took this idea right here, okay, and he moved it into the third dimension. Now he knew that we couldn't have a cube, right? A golden cube. And so what he did is he looked in the sea, and he knew that um, the pentagram that Pythagoras talked about had all these special properties. And he thought, well, what's a 3 dimensional equivalent of a pentagram? And so he looked at the decahedron, and he started to mess around, and he found out that as he used those around the eyes these decahedrons, and he positioned them around different places, and then he started to draw the lines in off of the decahedrons. He found out that he was able to create these two-dimensional proportions, these gold proportions, within a three-dimensional mask. So really, really creative, modern day, usable. Everybody uses this now I don't know everybody, but basically, this is the technique now for like plastic surgery, for today, or three-dimensional masks, no more the two-dimensional stuff. And so he calls it the golden ratio mask. And there's a website here, this beauty analysis. You can go in and read a lot about all the research that goes into this so-called beauty mask. And again, everybody's obsessed with beauty and all that, in advertising and movies and motion picture and things. And then a lot of them now refer to this. Again, it was grounded in thousands of years ago, creative ideas. And now we have math and art come together once again to move things forward, okay, from what they had been, sitting around for a long, long time. Now, there's just a little bit left here, so I am going to talk just for a few more minutes about this, and then you guys will work on this on your own. But this kind of ideas works with any proportioning systems. You don't have to use the golden proportions. You can create your own or use the standards. The golden proportions, the golden ratio was not the standard that everybody used. People used it. We know they talked about it. It's very well liked nowadays, but there still are standards like root 2 proportioning systems, root 3 proportioning systems, and there's root 5 and 7 and 9, so on. And I want to just show you very quickly the differences between the two, okay? And that's kind of where these questions, what they lead to. And so I'm going to go back to my board here. And now, so root 2 proportion, square root of 2, approximately equal to 1.414. Not a big difference from 1.618, right? Not a big difference. Root 2, why root 2? Well, I mean, really the paper sizing kind of pushed this one initially. If you take and draw a square, okay, draw a square, and again, it's not a great one, but again, we'll assume that's a square. And you go from the corner. Now, before when we did this one, we started with a square, and we started in the middle, went up here, dropped down the compass, extended this, right, and we came up with the golden rectangle. So this started in the middle. If you start at the end of a square and go up to the corner here and drop this down, okay, extend this out, all right, extend that down, you get a root 2 rectangle, okay. This is a root 2 rectangle, square root of 2, root 2 rectangle. So what's so special about a root 2 rectangle? If I take a root 2 rectangle, when they made paper years ago, okay, very expensive, very long, expensive process. You don't want to waste anything. They were very, very much against wasting any little bit, okay? So they use root 2 proportions because if I take a root 2 rectangle, cut it in half, okay, these two rectangles are now also root 2 rectangles. So if I have a big page for something very large, posters or whatever, I made posters that size, the big size. Then I cut it in half. Then I would use notebooks, maybe out of those, no waste. And then if I cut these in half, okay, I get 2 more root 2 rectangles. There's no waste. Now this becomes like a writing tablet or a smalling tablet or something. And then I cut it in half again, and maybe there's small little cards or something that we were making. Again, no waste. These are both root 2 rectangles. You can just keep cut them in half and cut them in half and go down and down and down until as small as you want or need without any waste. So everything gets used in that sheet of big, large paper that they press out of there and put together. So that is still, it's called the German sizing, ANSI sizing, DIN sizing, and so on, the DIN size. So that's still good today. Now, if I take this root 2 rectangle, okay, if I take again, let me just, I'll do right underneath here. So I take a root 2 rectangle, start with it, right? Root 2. And I draw from here, always up to the corner. Remember, this was a square I started with. I started with a square and then went down. Now this whole root 2 rectangle, I go down and I come down. Arc it down, draw this out. I get a root 3 rectangle. Root 3 rectangle. What's so special about a root 3? Well, again, just like this. If I'm working with thirds, any power of thirds, I take a root 3 rectangle. This is where people get the rule of thirds at, okay? Now, what's the square root of 3? Okay, square root of 3 approximately equal to 1.732. So if you notice, you have 1.414, 1.618, now 1.732. These are all very close. So a lot of people would say, use root 3 rectangle, right? Well, look how close root 3 rectangles are to the golden proportions, right? Very, very close. But see, a rule of thirds, they would always say use that. But basically what's happening is root 3 rectangles, if you divide them up into 3 pieces, these 3 rectangles end up being also root 3 rectangles. No waste. I can divide these up. These 3 rectangles here are root 3 rectangles. So 1, then 1/3, and then this would be 1/9. And I divide these would be 1/27, 1/81, 1/243. I can do the same thing. I can maintain my proportions. Everything looks nice and equal. When you proportion something out in a design, you really should keep the same proportions throughout. Everything looks then correct. Now, is that what everybody does? No, but there are no real rules. Let me just find this, and I want to finish with this. So what is the most sold print ever in the United States? Most sold print ever. Built on proportioning systems, okay, drawn with all proportioning systems. But this, supposedly, this Daybreak by Maxfield Parrish, you might have seen this. This says was the single most popular print in America, okay. Now, I've seen it. I've seen people have had. I didn't know it was the most popular, but if you get on through, this is just an example of you don't have to, in everything you do, keeps the same proportion because right here it shows you. Start with a square, go up and down, root 2 rectangle, go up and down that, root 3, root 4, 5, and so on. So actually, Maxfield Parrish used these different ones when he was putting his stuff together, and you can look and see even some of the original prints with the lines drawn on them when he was drawing this. So pretty neat. But so we don't want to do too much of that. We want to try to keep the proportioning system the same. And so assignment 4, draw something that exists in a real world using a proportioning system. You can create your own math-based system or use one of these ones from above, include your measurements. So that's the activity for this week. And hopefully you look at this and we'll, talk a little bit about some of this stuff during class time also, but mostly just this for this week. So that's kind of it for the video, and we'll see you guys in class.